So sorry about class today. If you weren't there, they had sprayed insecticides in the building right before or right as I was arriving, and I'm allergic to those, so I had to get out of the building. So anyway, this is what we would have covered in class. So today we're covering section 11.2, and then on Wednesday we'll cover 11.3. So 11.3 is one of the highlights of this class. It's the P versus NP. It's one of the, if no, it is. It's the biggest unsolved problem in computer science. So it's an important thing. And again, it's worth reading that chapter before class just to make it go a little easier. Okay. So 11.2 is about decision trees again. And for this, we're going to look at a device called a decision tree, obviously, that's going to help us to figure out the performance of some of the algorithms. Okay. Especially those that are comparison based. And many of the algorithms that we've talked about have a comparison somewhere along the way. Okay. So to take a look at what this can look like, let's take a look at what's on the screen here. We have a decision tree. And this one is you're trying to find the minimum of three numbers. Okay. So you have A, B, and C, or the three numbers. The first thing you're going to ask, you can only do a single comparison. You're comparing A with B. If A is bigger than B, you go to this side. If A is less than B, you go to this side. Okay. And then over here, you're asking, is A less than C? Okay. If A is less than C, then A is the minimum. If not, A was already less than B. So if C is less than that, then that must be the minimum. Okay. And same way over here, now we're saying that A is not less than C. Sorry, A is not less than B. Okay. So here you're saying is B is less than C. If it is, it's B. If not, it's C. Okay. So what this does for us, this looks at all of the possibilities. So any given trip through this is only going to take one path. Okay. So depending on the values of A, B, and C, we're going to either follow, one of the four paths that we have. Okay. Note that two of these paths have the same answer, C here and a C here. That's okay. Sometimes we'll have more outcomes or more outcomes than there are possible outcomes because you can get to the same outcome multiple ways. Okay. So what's interesting about these decision trees for comparison is that we can think about how long it would take to go through these trees. Okay. So these are binary trees. We're taking a comparison. Is it less than or not? Is it greater than or not? Okay. So we're only going to cover half of those. Okay. Half of the possible comparisons that we take. We're going to follow one of those paths. Okay. And from that, the book has this equation 11.1 that says that the height of this tree, it has to encompass all of the possibilities. They're binary tree, so it's a power of two. So we know that the height of the tree is greater than or equal to the ceiling of the binary log of L. Okay, L being the number of outcomes that are possible. Okay, so that's kind of the idea that we're looking at here. Okay, and the outcomes are represented as leaves because you're always going to have, that's what the L stands for. The leaf nodes where you're going to find the answer, basically. Okay. So this is going to become important as we look at things a little bit later. Okay. In fact, this is a similar concept that we just saw that instead of the showing the minimum, it's doing a sort. Okay. So in this case, we've got A, B, and C. We're going to check to see if A is less than B. If so, we go this way. Is A less than C? And then we have to worry since we're sorting, not just the minimum, there's this extra level of B less than C. Okay. And so forth to get to those. Okay. So we're looking at each of these states, what the current thinking on things must be. Okay. As far as the relative things, but the actual solutions are down here. Okay. So looking at equation 11.2, we can try to figure out how many possibilities we're going to have or how many outcomes we're going to have in the case of sorting. And then from that, figure out the minimum number of comparisons that we could make. Okay. So if we look at the um, string ABC, there are going to be 8 permutations of that. Okay. And we can get to that formulaically. Okay. On the number of permutations that we get. So 1, 2, there's only here three, four, five, six. There are a couple missing here, but there are still potential things here. Okay. So that is going to get us this idea that n factorial is going to tell us the number of permutations. And I think that makes sense. If you have the numbers 1 through 10, then what are the number of permutations that you have using each one once where order doesn't matter? You have 10 options for the first digit, 9 options for the second digit, and so forth. So 10 times 9 times 8, all the way down to 1 is 10 factorial. Okay. So looking at the inequality in 11.1, we get that the number of comparisons made, okay, that's the comparisons made is the height of the tree. So in any given run through, the number of levels that we go through will be the number of comparisons that we make to get to a leaf node that has the answer. Okay. So that can't be less than the log 2 of n factorial, okay, from that formula. Okay. So we have our inequality 11.2 that the C worst of n is greater than or equal to the log 2 of n factorial. Again, the ceiling of that. Okay. And we can use Stirling's formula here to get us an approximation or pretty good approximation of n factorial. So when you do that, okay, we do this little fun with math here, okay, and this ends up being approximately n log binary log of n, okay. So this is where we talk about the best possible theoretical performance of a comparison-based sorting algorithm is n log n. So that's where quicksort is in its best case, and where merge sort always is. Okay, so that's what we're getting at there. That's the idea from that one. Okay, so the book gives some more examples on how to do that using Stirling's formula and all of that. Okay, so in fact, I don't have the figure, but it's figure 3. I thought I'd copied it over, but apparently I didn't. In the book, talks about a decision tree for a 3-element insertion sort. Okay, so it's going to go through that particular way to figure out how that would work. Okay. There's also a section on decision trees for searching a sorted array. That just extends things out. It's not something that I'm particularly super interested in. Um, the one thing that is interesting is figure 11.4 that you can look up talks about this ternary decision tree instead of a binary decision tree. And with that, we're looking for something, is it less than, is it equal to, or is it greater than? Okay. For a binary search. Okay. And as the book explains, it turns out that um, the other search, the trinary search is not necessary. The equal just means that you're done. So you can turn it into a binary search, and then it will have the log or the n log n, which we expect. Okay. So I think that makes some sense as well. Okay. So this is a fairly small section. Okay. So actually not n log n. The binary search is just log n because you're cutting it in half every time. Okay. And that's the inequality 11.5 talks about that. Okay. So, I mean, I think that if you work through some examples, I had some we were going to do in class today, but they were certainly not necessary. I think you'll figure it out. So the homework for this time, I've already posted it, is going to be problem 1. It's going to ask you to do an inductive proof. So remember, with an inductive proof, you have to assume that what you're trying to prove is true for some case, okay? And then try to prove it for the plus one of that case, okay? And we've done inductive proofs before. If you're weak on that, you can certainly find some tutorials on it, okay? And problem 2 is going to be considering the problem of finding the median of a 3-element set with A, B, and C. It's going to have you draw a decision tree, go through that, okay? And then for problem 3, you're drawing a decision tree, find the number of key comparisons in the worst case and average case for the 3-element basic bubble sort. We talked about bubble sort before. And then the 3-element enhanced bubble sort, okay? And the enhance, I think we've talked about, and it says it here. Basically, it stops if there are no swaps made, so it doesn't keep trying to sort even after it's already sorted. Okay. And then problem four, you're going to design a comparison-based algorithm for sorting a four-element array with the smallest number of element comparisons possible. Okay. So since it's only a four-element array, you have some extra things that you can try there. Okay. So that is decision trees. I think it's relatively straightforward, relatively basic kinds of stuff. Um, if you have trouble with the homework or whatever, let me know. We can talk about it at the beginning of class on Wednesday if you want. If not, we will keep moving on.